Now that we have the functional scaffold, we can perform an on-rate experiment. To avoid the formation of aggregates caused by streptavidin molecules linking multiple scaffolds, we work at low construct concentrations. The important thing is that the concentration of the construct should be lower than the effective concentration of the two biotins in the scaffold, which in the case of vars 4 and 8 is roughly 30 nanomolar. The construct prepared previously is at a concentration of 16 nanomolar. To ensure that aggregation is not an issue, we will dilute this 100-fold. To avoid capping, or the binding of two streptavidin molecules to one construct, thus rendering that construct unloopable, the streptavidin concentration should also be well below the effective concentration of the ligands on the scaffold, which for vars 4 and 8 is roughly 30 nanomolar. To achieve this, we will dilute the streptavidin to roughly 6 nanomolar, so that when mixed in equal volumes with the scaffold, the final concentration of the streptavidin is 1/10 the effective concentration of the two biotins on the loop. 1 mg per ml streptavidin has a concentration of roughly 15 micromolar. Diluting this 2,500-fold will bring the streptavidin to a nominal concentration of 6 nanomolar. We measured the concentration of our streptavidin and its activity using a HABA assay, and found that our results closely match the data sheet provided by Rockland, yielding an effective final concentration of streptavidin of 6.8 nanomolar, which when mixed 1-to-1 with the construct, this yielded a streptavidin concentration of 3.44 nanomolar. Dilute the construct 100-fold to achieve a concentration of 160 picomolar. Note, if you used oligonucleotides at lower concentrations, your construct may already be less concentrated than 16 nanomolar. If you use different volumes in creating your construct, you must calculate the final concentration of your sample. In an Eppendorf protein low-bind tube, mix 1 microliter of your construct with 99 microliters of the buffer in which you wish to do the experiment. One buffer condition that we recommend for the biotin streptavidin experiment is 1x NEBuffer 2, supplemented with an additional 150 millimolar sodium chloride. To make 2 mils of this, mix the following: 200 microliters of 10x NEBuffer 2, 100 microliters of 3 molar sodium chloride in nuclease-free water, and 1,700 microliters of nuclease-free water. Next, we will dilute the streptavidin 2,500-fold in an Eppendorf protein low-bind tube. Mix 4 microliters of 1 mg per ml streptavidin with 196 microliters of the same buffer used to dilute the construct. This yields a roughly 300 nanomolar stock of streptavidin. In another Eppendorf protein low-bind tube, mix 4 microliters of the 300 nanomolar streptavidin with 196 microliters of the same buffer. This yields a 6 nanomolar stock of streptavidin. This low concentration should be made fresh before each experiment. To do the on-rate measurement, equal volumes of 160 picomolar construct and 6 nanomolar streptavidin will be combined. Loops will immediately start forming. To halt the loop formation, the construct can be quenched with free biotin to occupy all of the free sites on streptavidin, thus preventing further loop closure events. If fractions of the construct are quenched with biotin at different times, this yields an on-rate time series. The rate of loop closure with 3 nanomolar streptavidin and 80 picomolar scaffold saturates after roughly 2 minutes. A good series of time points to cover this range well in seconds is 5, 10, 15, 20, 30, 40, 60, 80, 120, and 360 seconds. As you will only have 5 seconds between the first couple of time points, you will want to prepare all of your tubes and quenchers before starting the experiment. We will provide a very detailed approach to doing these experiments, which we have found greatly facilitates performing on-rate measurements. To prepare the biotin quencher, you'll want to make a saturated solution of biotin, 0.22 mg per ml, or roughly 1 millimolar, in nuclease-free water. To ensure that the solution is saturated, we recommend having excess powder in the tube. The tube can be vortexed and then centrifuged before each use. Please note that this procedure can take a couple of tries to nail, especially the early time points. We recommend practicing with empty tubes to get the timing and positioning down. Additionally, having more time between samples such as 10 seconds rather than 5, may help for the first couple of experiments. We have also found that doing the experiment on parafilm can help with speed, but we tend to prefer using low bind tubes. Let's now perform an on-rate experiment with the above-mentioned time series. 10 Eppendorf protein low bind tubes should be labeled and arranged in an easily accessible manner in a tube rack. 2 microliters of the saturated biotin solution should be pipetted into the very bottom of each tube. But during the on-rate experiment, it will help save time to leave all of your tubes open. We recommend having an ample supply of 1 to 200 microliter low bind tips and 3 pipetters at hand, 1 that can pipette 60 microliters and 2 that can pipette 10 microliters. Add 60 microliters of the 160 picomolar construct to a new protein low bind tube. Load tips onto all 3 pipetters and have them close at reach. Set a timer that counts up after the alarm rings for 30 seconds. Aspirate 60 microliters of the roughly 6 nanomolar streptavidin mixture into the pipette. Be sure not to handle the tube near the bottom, as this will heat the sample to your body temperature, yielding an artificially higher room temperature on rate. When the alarm sounds, mix 60 microliters of the streptavidin with 60 microliters of DNA. Grab the first 10 microliter pipetter and aspirate 10 microliters of the mixture. When the count-up timer hits 5 seconds, pipette the mixture into the bottom of the 5-second tube. Now continue with the remaining time points, changing tips between samples.